Good day, I'm J Wildberger. In our last video we introduced a simpler notion of a limit. We were able to do that because we're focusing on rational polynumbers as the primary objects, the initial objects in calculus. The definition was the following. Suppose that P is a rational polynumber, and that means pretty well the same thing as a rational function in the usual terminology, and that A is a rational number. Then the limit as n approaches infinity of P of n equals A, this means the following. So we're defining what this means. It means that we can find two natural numbers m and k, so that if n is bigger than or equal to m, then this inequality holds. The inequality is that the difference between P of n and A is bounded on either side by k on n and minus k on n. So this should be true for all natural numbers n which happen to be bigger than m. So these numbers m and k, we refer to them as the start and the scale, because m is the start, so that's sort of the place where the inequality starts for all n starting from there. And k is the scale because it sort of determines what the scale of the bound on the difference should be. And these are certificates for the limit in the sense that they're documents that we can present that verify, that substantiate the claim that the limit of P of n is equal to A. This is our definition of the limit of a rational polynumber being equal to a certain rational number. And it's a lot simpler, both in theory and in practice, to the standard definition that you find in all calculus texts, which in fact students struggle with and which is often not really taken seriously in most courses, unless it's a sort of a high-level course. But I think this definition is accessible to even ordinary students. The logical structure is not that difficult, and we'll see that in practice it's not too hard to work with this. And we can get a good visual understanding of what a limit means by approaching it from this no-nonsense point of view. So first let's make the observation that the basic inequality on the previous slide that had a star beside it can be rewritten in this form here. So all that we've done is we've moved the minus a, which was inside here, so we used to have P of n minus a, and we've added a to all sides so that now there's an a on this side and there's an a on this side. This is another way for us to see that P of n is sandwiched between a plus something and a minus something. That's another way of thinking about what the limit means. Okay, so here's a picture that tries to illustrate what's going on. So we have n in this direction here, and we have a sequence and P of n, and we're just giving rather arbitrary values of the sequence. Here they are right here, these black and blue dots. And here is the value a, which in this case happens to be 6. There's the value 6. And in this case here we're trying to illustrate the idea that the limit as n approaches infinity of P of n happens to be 6. So if we want to illustrate that, it means we have to find an m and a k so that this inequality is satisfied. That 6 minus 4 over n is less than or equal to P of n, which is less than or equal to 6 plus 4 over n. So in other words, P of n is sandwiched between 6 plus 4 over n and 6 minus 4 over n. And what that means geometrically, well, there's the value 6. And here, this hyperbola branch represents 6 plus 4n. So when n is 1, 6 plus 4 over n is 10, so there it is there. And when n is 2, we have 6 plus 4 over 2, which is 8. And then here is 6 plus 4 over 3, 6 plus 4 over 4, 6 plus 4 over 5, and so on. And as n gets bigger, 6 plus 4 over n converges, approaches 6, because the 4 over n term goes to 0 as n gets big. On the other side, we have 6 minus 4 over n. So that when n is 1, we have 6 minus 4, which is 2 down here, and then 6 minus 2, which is here, 6 minus 4 over 3, 6 minus 4 over 4, 6 minus 4 over 5, and so on. Those are the values of 6 minus 4 over n, the left-hand side. And so this inequality is just telling us that we want p of n to be within these bounds, to be between 6 minus 4 over n on the bottom and 6 plus 4 on n on the top. So this sequence is not always inside this region, but it is inside the region after a certain point. So if we start with 8, after 8, it certainly looks like all the terms of the sequence are sandwiched between these two arms, these two hyperbolic arms, which approach 6. And so 8 is our starting point. 8 is the number m. So the claim is that if n is bigger than or equal to 8, in other words, if we just look from here on, then yes, indeed, the sequence's values are satisfying this inequality. So m equals 8 is the start, k equals 4 is the scale, and if we change the scale, what would happen is that the hyperbola would go up or down. It would be wider or narrower. So if we increase k, then the hyperbola becomes wider apart, still maybe at arms like this or arms like this. And if we decrease k, then it becomes closer to the green line. So this is quite different from the usual calculus notion, because once and for all we're choosing an envelope. There's only the one envelope given by 6 minus 4n, 6 plus 4n. It doesn't change. There's no epsilon dependence here. We're looking for a fixed envelope that contains the sequence. And the envelope is completely characterized by these two numbers, k and m, which in this case are 4 and 8. So it's a relatively simple and I think easy to understand geometrical situation. The idea of the limit of a rational polynumber sequence. So in my last video I gave you some exercises with limits, and I want to have a look at those exercises today. So let's go over them. The first one was to show that the limit as n approaches infinity of 1 over n plus 1 is 0. Okay, intuitively, yes, this makes sense. This is quite reasonable. We want to see that the actual definition corresponds with our intuition. So according to the definition, what we need to do is we want to find m and k, natural numbers, that have the following property. That if n is bigger than or equal to m, then the difference between these two things, which is 1 over n plus 1, is sandwiched between k over n and minus k over n. So that's our job, to find an m and a k. That's all we have to do, find those two natural numbers. And they're not necessarily unique. So we need to find some natural number m and some natural number k, so that when n is bigger than or equal to m, then this inequality is true. So we look at this inequality and ask, well, when is this true? What value of k do we have to put in here so that this is true for some values of n past a certain point? Well, 1 over n and 1 over n plus 1, they already have a relation. But 1 over n plus 1 will always be less than or equal to 1 over n. Because as the denominator gets bigger, the fraction or the rational number gets smaller. So if we have a k equal to 1 here, then this is going to be automatically true, this right-hand inequality. And the left-hand inequality is true automatically because that's always a positive quantity. Remember, n is a natural number throughout. And this is always negative. So that's sort of automatic. So it's very simple. We just choose m equals 1 and k equals 1 since, and then we can write it, if n is bigger than or equal to 1, then minus 1 over n is less than or equal to 1 over n plus 1 is less than or equal to 1 over n. Right? This is a true statement if n is a natural number bigger than or equal to 1. So we found our m, we found our k, we found the start, we found the scale. These are the certificates required. We can assert that according to the definition, the limit as n approaches infinity of 1 over n plus 1 equals 0. So the second example was the limit of 1 over n squared, which is also 0. So what do we want to do? Well, here's the inequality that we want to prove. The difference is 1 over n squared. It's got to be between k over n and minus k over n. And that's got to be true when n is bigger than or equal to m. So we have to find m and k, so that's true. So then we look at this and say, well, when is this kind of inequality true? This is always positive, that's always negative, so this is automatically true. We don't have to worry about that. How about this inequality? Well, 1 over n compared to 1 over n squared. How do you compare them? Well, n squared is bigger than n, just like n plus 1 is bigger than n. So 1 over n squared is less than or equal to 1 over n. We can get away with putting k equals 1. So if m is equal to 1 and k is equal to 1, then for any natural number, n, this inequality is going to be true. Therefore, the limit as n approaches infinity of 1 over n squared is 0. So far, all the examples are very simple with the start and scale both being equal to 1. All right, let's have a look at the third exercise I gave you, which is a little bit more challenging. The limit of 1 plus n over 2 plus n, as n goes to infinity, is equal to 1. All right, so here the rational polynumber that we're talking about is 1 plus alpha over 2 plus alpha. So we want to find a number m, a natural number called the start, and another natural number k, called the scale, so that if n is bigger than or equal to m, then the difference between the sequence and the limit is sandwiched between k over n and minus k over n. So we have to have a look at what's inside here. 1 plus n over 2 plus n minus 1. We can get that over a common denominator, and it becomes minus 1 over 2 plus n. So the inequality that we want to satisfy is now minus k over n is less than or equal to minus 1 over 2 plus n is less than or equal to k over n. And there are really two inequalities here. We have to have this satisfied, and we also have to have this satisfied. And let's just remind ourselves that all of the quantities inside here are natural numbers, like 1, 2, 3, 4, 5. So we want this to be true for all n bigger than or equal to some m. And we have to choose k appropriately to make that happen. So here are the two inequalities. The left-hand one, the right-hand one. The right-hand one holds automatically because now this quantity is always negative because there's a minus sign here, and n is always a natural number. So this is always less than 0. And the right-hand side is always positive, so that's going to hold automatically. We only have to think about this left-hand inequality. Okay, so let's have a look at that. So it's minus k on n is less than or equal to minus 1 over 2 plus n. We want to rearrange this so that it's a little bit easier to work with. Well, we can take this thing to the left-hand side and this thing to the right-hand side so that the minus signs disappear. So if we bring minus this to the other side, it becomes plus 1 over 2 plus n. And we bring this to the other side, then we get plus k over n. So this is equivalent to the inequality 1 over 2 plus n is less than or equal to k over n. Well, these two numbers are positive, so this inequality is equivalent to this one here, where we've multiplied through by the common denominator, which is positive. So n is less than or equal to k times 2 plus n. K is a natural number, n is a natural number. This was automatically true for any natural number, because 2 plus n is bigger than n, and k is at least 1. So it's automatically true. That means we can choose m equals 1 and k equals 1, and then for any n bigger than or equal to 1, then this inequality, this one here being replaced by this one here, will automatically be true. So we conclude that the limit as n approaches infinity of 1 plus n over 2 plus n is equal to 1. And it was important for us to put a 1 here. If we had put anything else here, then this inequality would not have worked. You can perhaps think about that. So all the examples so far, in some sense, have been very straightforward. We haven't had to do a lot of subtle thinking at all. All the scales and starts have been 1 so far, because we've had relatively simple examples so far. Clearly, we're going to have some skill in dealing with inequalities when we work with this limit concept, because we're going to have to manipulate inequalities. In fact, inequalities are crucially important for analysis generally. And it's important, therefore, for us to review the basic foundations of inequalities. This is a subject that we haven't talked too much about in this series, so maybe here's a chance now for me to fill in some gaps. So let's talk a little bit about inequalities for the rest of this video. Let's start with the simplest case, when we go right back to the natural numbers. And in fact, to the first video in this series, which I hope you've all watched, Math Foundations 1. And the question that arises is, how do we compare two numbers? This is a very primitive situation where a number was represented just by a bunch of strokes on a page. So suppose one person writes a bunch of strokes there, and someone else comes along and writes some other ones. Both of them are numbers. Which one of them is bigger? Well, before we are able to count, before we've given names to numbers, we can still figure out which one is a bigger number by doing the following. By pairing them up. Matching this one with this one. Maybe you can think of them as twigs. This twig matched up with this one with this one. These two, these two, these two, these two, these. And now we see that this first number has 2 left over. So it's the bigger number. Right? That's how we can decide that m is bigger than n, even if we cannot count. Of course, with our more advanced notation, we would say that this number n plus 2 equals m. And that allows us to conclude that n is in fact less than m. So here's a definition of the inequality. What does it mean for m to be less than n? For natural numbers m and n. Well, it means that n is equal to m plus k for some natural number k. If we can get from m to n by adding something, then m has to be less than n. Or n is greater than m, same thing. Okay, so having made that definition, we can now do a few exercises. And I'm going to leave most of the details here to you. So I'll show that if L, M, and N are natural numbers, and L is less than M, and M is less than N, then L is less than N. Similarly, show that if we have 3 natural numbers, K, N, and M, then if M is less than N, and we multiply both of them by K, then K times M is less than k times n. In fact, you could also show that k plus m is less than k plus n. That's probably something else we should include as something to do. So very basic manipulations with inequalities for just natural numbers to start with. So now let's fast forward to integers, which were introduced in Math Foundations 12. And I hope you've all watched that. So let me remind you that an integer, a, was defined in terms of a pair of natural numbers. We said that if we had an expression m less n, so this little forward slash is read as less m less n, we agree that m less n is equal to p less q, and these are all natural numbers, precisely when m plus q equals n plus p. So the meaning of it is a lot like subtraction. If you just move that a little bit further, it's really like m minus n equals p minus q. But this is before we've actually defined subtraction. Okay. That's how we define a notion of an integer, an inequality between two representations of an integer. Alright, so now we can define inequalities for integers. Here are two integers, m less n and p less q. What does it mean for this one to be less than this one? For a to be less than b? Well, it means that m plus q is less than n plus p. They're equal when these two quantities are equal. But if this one is bigger than this one, then we say that b is bigger than a. So this expression reduces to knowing the inequality for natural numbers. So the inequality for integers is dependent on the inequality for natural numbers, which is only fair. And I remind you that we introduced the special integer 0 as 1 less 1, or 2 less 2, or 3 less 3, etc. And we can also define the negative of an integer. The negative of m less n is, order reversed, n less m. Okay, so now we can introduce the important ideas of positive and negative integers. So we're working here in the integers. A is an integer, then it's deemed to be positive, written this way, 0 less than or equal to a, or a greater than or equal to 0, precisely when a is bigger than 0 or a equals 0. So in here we've defined what it means for one integer to be strictly less than the other. We're saying that a is positive if it's strictly bigger than 0 or if it's equal to 0. This is not entirely standard notation. Half the world treats positivity with an equal sign, and the rest, the other half, treats it without an equal sign. So it's a bit of a debate. I prefer to think of positivity as including 0. All right, so let's adopt that policy. 0 is a positive number according to this definition. And negative numbers are symmetrical. So a is negative precisely when a is less than or equal to 0, and that means that a is either less than 0 or it's equal to 0. So positive and negative are exactly symmetrically defined. Of course, that means that 0 is both positive and negative. That's all right. Then a number is strictly positive, a, when it's greater than 0. And it's strictly negative when it's less than 0. So positive, negative, strictly positive, and strictly negative. I'd like to remark that what we are calling positive is often these days called non-negative. This is a word that's quite often used, and I think it's unfortunate because it contains this double negative to talk about something which is more simply expressed with a single positive. So I'm going to try to avoid the use of non-negative and I urge you to do the same. It's not necessary. Positive and strictly positive suffice to describe quite clearly the two possible situations there. Okay, then another exercise, that if a, b, and c are integers, then if a is less than b, then minus b is less than minus a. If a is less than b and b is less than c, then a is less than c. If a is less than b and c is strictly positive, then a times c is less than b times c. On the other hand, if a is less than b and c is strictly negative, then b times c is less than a times c. So the order of the inequality reverses when you multiply both sides by a strictly negative number. And we also agree that we'll be flexible about the choice of inequality. So a is less than b. That means exactly the same as this thing here, which we could read as b is greater than a. All right, so they're exactly the same meaning. Okay, so now let's move up to the rational numbers and introduce inequalities in that context. And of course it's dependent on the prior notions for natural numbers and integers that we've already introduced. So p is a rational number, means it's of the form a over b, where a and b are integers, and b is not equal to 0. And I remind you that we have this notion of equality, that a over b equals c over d, precisely when a d minus bc equals 0. Okay, so let's start by introducing a notion of strictly positive. So the rational number p, or a over b, is strictly positive. In other words, it's greater than 0. What does that mean? Well, it means that a and b are both strictly positive integers, or a and b are both strictly negative integers. We have to deal with the fact that a and b are not unique. We can multiply both a and b by any non-zero number and get an equal rational number. In particular, we could multiply both of them by minus 1 and the rational number hasn't changed. If we multiply both of them by minus 1, then this total condition doesn't change. We might go from this condition to that condition, or from that one to that, but the whole condition doesn't change. So this unambiguously defines what a positive, strictly positive rational number is. Now we can define when one rational number is less than another rational number by agreeing that that happens precisely when the difference, c over d minus a over b, is positive. So we can define inequality in terms of our notion of positivity. Okay, and then there's various things that one can show along the lines of the previous kind of exercises. So I'll leave it to you that if you have, say, 4 rational numbers, p, q, r, and s, then if p is less than q, if we add r to both sides, then p plus r is less than q plus r. If we subtract r from both sides, p minus r is still less than q minus r. On the other hand, if we multiply by something that's strictly positive, then, well, the order doesn't change, so p times r is still less than q times r. Or if we divide by something that's strictly positive, then p over r is still less than q over r. However, if we try the same thing with something that's strictly negative, we have to swap the order, just as we saw for integers. So if p is less than q to start with and we multiply by something strictly negative, then we have to interchange the order so that qr is less than pr. And that also happens if we divide by r, so q over r will be less than p over r. And then p less than q and r less than s, we can add those two inequalities to get p plus r less than q plus s. And very likely there are a few more that I haven't thought up here. So I don't want to minimize the importance of this. It's actually quite important that one understands inequalities very well, and that somewhere this is all laid out and given nice consistent proofs for. So we're not going to do that because we're a little bit impatient to get on to limits and talking about the problems with real numbers. But I don't want to slight this, the importance of this topic. Inequalities are very important in mathematics, and having some place where this is all laid out very clearly and pleasantly would be a great thing. Later on in this course, I'm going to talk about a proposed project where I'm going to try to encourage people to start working together to create a framework, sort of a wiki framework for mathematical foundations. And so I'm hoping that some of you will help at that point and actually write down details of things like this in a public domain, lots of links where everyone can check things and where we can actually become much more confident about the foundations of mathematics. So I think this is seriously missing up till now, and it's an important goal that we'll talk about later on in this course. So that's at least a bit of a review, or an introduction perhaps, to inequalities, and these are important tools when we're working with limits, which is what we're interested in doing right now. Right, so here are some exercises for you. A little bit more sophisticated now, a little bit more complex limits. So show that the limit, as n approaches infinity, of 2 plus 3n over 1 plus 2n equals 3 halves. The limit of 1 plus n squared over 1 plus 2n cubed equals 0. The limit of 1 plus n squared over 1 minus 2n plus 5n squared equals 1 over 5. And in this case here, I'm asking you to find the limits. I'm not telling you what the limit is and asking you to prove it. I'm asking you to, first of all, find the limits. So find the limit as n approaches infinity of minus 1 plus 3n over 2 minus 4n. And the limit as n approaches infinity of 5 minus 2n squared over n plus n squared. And once you've found the limit in some way or another, show that that actually is the limit by going back to the definition. So for example, to come up with this 3 halves is not too hard. You just imagine what happens if n is a very, very big number, like if n is 1,000. If n is 1,000, this is 3,002 divided by 2,001. That's pretty close to 3 over 2. And we can imagine in our minds very easily that if n is very big, this 2 and this 1 are almost insignificant. It's almost like 3n over 2n, which is 3 halves. But that's not an argument to prove that the limit is that. That just suggests that the limit is 3 halves. The official definition requires certificates. Requires that you give me an m and a k, and that you verify the crucial inequality that bounds the difference between the sequence and the limit. Alright, so good exercises. A little bit more algebraic skill and working with inequalities is going to be required here. Next time, well, we want to go further. We want to start talking a little bit more about these higher degree rational polynumbers and limits for them. And we also want to address the issue of what happens when you don't have an n squared over an n cubed, but an n cubed over an n squared, say. In which case the limit in some sense is going to infinity. So we want to talk about what does it mean for such an on sequence to go to infinity. I hope you'll join me for that. I'm J Wildberger. Thanks for listening.